In this video, we'll be discussing Taylor and Maclaurin polynomials. This is from the first part of the section 6.3 out of the OpenStax Calculus book, Volume 2. In that section, Taylor and Maclaurin series are discussed, but it makes more sense to talk about the series after we first talked about the Taylor and Maclaurin polynomials. Now, Taylor and Maclaurin were both mathematicians. Taylor was British and Maclaurin was Scottish. They did a great deal of work in sequences and series, and these are named for them for that reason. However, they're almost certainly not the first people to have discovered these series. They're simply the first people to have written it down and been published. That often happened in historical times, that it was the person who wrote them down and published the information who got the credit for the information. Let's talk about what a Taylor or Maclaurin polynomial is. First, we want to start with the idea of approximating a function with a polynomial. In the center of the screen here, you'll see that we have different polynomials. We have a degree 0 polynomial, which is just basically a constant, and a degree 1 polynomial is, of course, just a line. Degree 2 is a parabola, degree 3 would be a cubic, and so on. In general, when you get up to the nth degree polynomial, you can write it as a finite sum where you let c sub k represent the coefficients of each variable term, and you let x to the kth power be the variable. Now, if you allow this to go to infinity, this will give you a power series, which we discussed earlier in the previous section. What we want to know is, if we do approximate a power series with a finite polynomial, what does this mean, both on a graphical sense and in an algebraic sense? In other words, if instead of using the entire power series for a function, what if we only did the first finite number of terms, for example, the first n terms, and used that to approximate the infinite power series? I'd like you to think now about the linear approximation function that you learned about in Calculus 1. In the linear approximation function, this was basically the tangent line at a particular point on the graph. The point on the graph was usually given as a, f of a. So for example, if we were looking at a graph, we had a point on that graph, a, f of a, and we could approximate a differentiable function as long as we stayed close to a with the tangent line at that point. Now, the reason this worked is because if it's differentiable, then you know on the graph that you don't have any sharp corners or sharp cusps and no vertical tangent lines. Because there are no corners and cusps, if you use a microscope and you go in closer and closer to the graph, no matter how curvy it is, if you go in close enough and it's differentiable, it will eventually start to look like a line. And if you're close enough to A, then that curve will be close enough to the graph of the tangent line at A. We called this the linear approximation function, or capital uppercase letter L of x. You'll see here in the center that we've written the equations both in terms of y and in terms of L. Remember, this just comes from the point-slope form of a line. Y minus y1 equals mx minus x1. Our x1 is a and our y1 is f of a. So this gives us y equals y1 plus the slope, which is of course the derivative at a, times x minus x1. This is the same equation, but with y replaced with L of x to represent the linear approximation function. Now, this polynomial does have some important properties. It matches the original curve f in both the value and the slope at the point x equal a. In other words, the derivative at a is exactly the same value as the slope of the tangent line at that point. They also both contain that point a of f of a, so they have that in common. In addition, close to that point, they both have to be increasing, since the first derivatives will match sign, or both decreasing, again because the first derivatives match in sign. We can call this linear approximation function p sub 1, or representing the first polynomial approximation. The 1 represents the idea that it's the first derivatives that match values at a f of a, where the two functions are touching. Now let's look at what this means on the graph. On the left, you'll see a curve f of x, which represents the rational function 1 divided by x. It is a curvy function, though not as curvy as some. You will also see that they've chosen the point x equal 2 to serve as the a value. What they did was they found the slope of the tangent line right there at 2, and they graphed the line here, the tangent line, at that point. This must be the point 2, 1/2, because when x is 2, the y value on this function would be 1 divided by 2. That's where the 1/2 comes from, and the 2. The negative 1/4 is the derivative of the function 1 divided by x evaluated at x equal to 2. That's where you get the negative 1/4. If you look inside this little rectangle and you imagined using a microscope or a magnifying glass to get closer to it, you'd get a picture like you see here on the right. On the right, you can see that you've zoomed in so close to it that you can hardly tell the difference between the curve, that is the orange line, and the tangent line, that is that dark blue line. In other words, they both look like lines as long as you are relatively close to the value x equal 2. And you can see down here on the x-axis what we mean by relatively close. You'll see that these are within, in general, 0.04 of this value. That's quite close. But as long as we're there, I can approximate the value on the function in orange with the value on the tangent line in blue, and they'll be relatively close. This is the linear approximation function. In this case, you'll notice that the original function is decreasing at x equal 2, and that the tangent line is also decreasing there. In fact, their derivatives at 2 agree exactly on the value, which is negative 1/4, and they both have in common the point 2, 1/2. If you look at a different kind of linear approximation, where the graph is not a rational function and instead you were looking at, say, a parabolic function, on this particular graph, you'll see that they've chosen this value to serve as a, and this y value is the value you get out of the parabola when you plug in a. That means that both the curve in black and the tangent line in red share the point a f of a. It also means that they have exactly the same derivative value at x equal a. And in fact, since the tangent line is increasing at that point, we know that in fact the parabola must also be increasing at that point. This is again a linear approximation function. It doesn't appear to be quite as good as the one above, but then we are not pulled in very close like in a microscope or magnifying glass situation. Let's think about when this might be a good approximation for the function f. It will be a good approximation if f is not as curvy. That means that the function has a fairly constant slope close to the point x equal a and y equal f of a. On the other hand, if this is a curve that wiggles around a lot and changes curvature a lot, then the tangent line will not be a very good approximation once you get far enough away from a. To remedy that situation, we can instead create a quadratic equation, which is curvier than a line, and use that to approximate the polynomial by adding another term to the line. Remember, the difference between the equation of a line and the equation of the quadratic is the ax squared term from the quadratic. We'll call this second polynomial, the quadratic one, p sub 2 of x, and we will ensure that the second derivatives at the same point, a f of a, also agree where the two functions touch. Again, the 2 in the subscript is now because not only are we going to make sure that the first derivatives match at the single point a f of a where they touch, but also that the second derivative will match there as well. In other words, if the original function is increasing, the first derivative will guarantee that it is also increasing. But in this case, doing P2, or the second approximation, the quadratic one, guarantees that the quadratic is also concave up, just as the black curve was originally concave up. This will give us a better approximation. If you look at the graph here, you can see that the red line is peeling away from the black, and you can see space between them much sooner than the blue quadratic equation peels away from the black curve. And you can see the space between the black and the blue. In other words, there is a wider interval over which it appears that the quadratic is a better approximation. So for example, if I wanted to mark those, it looks to me like this is a good point where I can't see the difference between the quadratic and the black curve that we have for a function. On the other hand, for the line, I've got to be much closer. I can see the red line peeling away from the black curve that early on the left and even earlier on the right. In this way, by adding another derivative to agree at the point a f of a, we get a wider interval around a over which that quadratic, the blue curve, is a good approximation for the function which is in black. And we'll call that P2. Here's what the equation for P2 would look like. What we added was simply the quadratic term represented here by C2 times x minus a quantity squared. The a here is the same a that we see in the graph above. You'll notice that we have added that onto what is actually the linear approximation function. So in other words, all we added was one additional term, the quadratic term. If we let x equal to a, then we can find that the second polynomial approximation at a becomes f of a plus f prime of a, same as here. Now substitute a for x, a minus a, plus c2 times a minus a. Well, a minus a, of course, that goes to 0. So since these both go to 0, that lets us then write that at the point a, the values agree, and that meets condition 1, that the point a f of a is on both graphs. So that is our condition 1, a f of a on both curves. And by both curves, we mean f of x and P2 of x. What about the second condition? The second condition would be about the first derivative. In order to do that, let's take the derivative of the function up here at the top and see what that leads to. By applying the derivative to this representation for p sub 2 of x, the derivative of f of a, which is a constant y value, of course goes to 0. In that case, we'll look at the next term. If I were to distribute f prime of a, which is also a constant representing the slope of the linear approximation function, this would give me a constant times x and then a constant times a constant. The derivative of the constants will be 0, but the derivative of the slope times x will just be the slope or f prime of a that you see here. For the last term in p sub 2 of x, we need to take the derivative of the quadratic term. This requires the chain rule. Remember to pull the 2 to the front to multiply by the coefficient constant c sub 2. That gives us 2c sub 2. Reduce the power on x minus a by 1, and then multiply by the derivative of the inside. Since we're taking the derivative with respect to x, and a is known to be a constant, the derivative will be 1, so it doesn't need to be written. This will represent the first derivative of p sub 2 of x. To make sure that the first derivatives match at a f of a, we'll let x equal a again and plug that into the first derivative equation. Replacing x with a will not change the first part since that was a constant to begin with, but it will replace the variable x in the second term with an a. Because a minus a again goes to 0, this tells us that the first derivative of p2 at a is equal to the first derivative of the function at a. This is our second condition, that the first derivative of both functions at a is the same. Now let's check the third condition. The third condition is the second derivative of both functions at a f of a must also be the same. Let's take the derivative of this line representing the first derivative of p sub 2 to get the second derivative of p sub 2. Since the first term is a constant, the derivative again is 0. In the next one, x minus a, only the x is the variable, so the derivative will simply be its coefficient, 2c2. That will lead to the conclusion that the second derivative of p2 at x will be a constant, 2c2. To make the third condition be met, we need the second derivative of p sub 2 to be equal to the second derivative of the function at a. That means that the second derivative of f at a must also be 2c2. Then we can solve for c sub 2, and we find that c sub 2 is 1/2 the second derivative at a. Now we can write an expression or an equation for p sub 2 that will meet all three conditions. Condition 1, the 2 points or the two curves share the point a f of a. Condition 2, the first derivative of both curves are the same at a f of a. And condition 3, which is here, is that the second condition, or second derivative, of both curves at the point f of a are also equal. This will give us a better approximation, as we saw in the last one. As you can imagine, you can do this over and over and over, finding higher and higher degree approximating polynomials. We will always require the value of the derivative at the approximating function p sub n to be equal to the same derivative of the original function f at the point where the two curves touch, which is the point a f of a. In general, the third approximating polynomial, and I can see I have an error here, which I will fix in just a second, this should be p sub 3, is given by this equation here. You'll see that the first two terms make up the linear approximation function. The third term is adding in the quadratic term, and the fourth term is adding in the cubic term. Let me correct that error now before we proceed. So what I corrected was I relabeled this as p sub 3 because it is the cubic approximating polynomial. In general, if we continue this practice, can you see that there is in fact a pattern developing? You'll notice that in the second, third, and fourth terms, we have a first derivative, then a second, then a third derivative. That also matches the power on the binomial factor x minus a, the first power, the second power, and the third power. In fact, it matches the denominator of the fractions, the third factorial, the second factorial, and if we continue the pattern backwards, this should be the 1 factorial, which is of course 1. Does this fit the first term? It will fit the first term if we consider the zeroth derivative to be the function itself. In other words, the zeroth derivative, you haven't actually done the derivative. Since 0 factorial is defined to be 1, and since x minus a to the 0th power is also 1, this pattern fits. Let me show you what this term would look like if I were to rewrite it in that format. F of a can be written in the following format to make it fit. To indicate the 0th derivative, I must put the 0 in parentheses. Otherwise, it represents a power. That's the 0th derivative at a, meaning don't do the derivative at all, divided by 0 factorial, which is defined to be the number 1, times the binomial factor, x minus a raised to the 0th power, which is also the number 1. So in fact, we've come up with a formula. This gives rise to what are known as Taylor polynomials. The definition for a Taylor polynomial is given by that formula. Different books write it differently, but it is often the case that we separate the constant pattern from the rest of the pattern to emphasize the fact that this is some coefficient constant multiplied by the binomial factor x minus a raised to the kth power. You get the constant factor by taking the kth derivative of the function, plugging in the center a, and then dividing by k factorial. You'll notice that up above, that is exactly what happened when we wrote out the terms for the first 3 approximating polynomials. The notation, again, with f and parentheses around the number above it in the power position, represents the nth derivative of f. By definition, the 0th derivative is the function itself. In other words, f to the 0th derivative is f of x. Let's use what we learned in the previous examples to write out what's called a Maclaurin polynomial, the first 7, P1, P2, P3 up to P7, for f of x equal to sine x. Now you may be saying, but wait a minute, we didn't define a Maclaurin polynomial. You've only been talking about Taylor polynomials. I don't know if it said it. It did not. So I need to make it clear that a Maclaurin polynomial is a Taylor polynomial where the center is equal to 0. So let me write that down for you now. A Maclaurin polynomial equals a Taylor polynomial, and the center, which is also called a, is 0. In other words, all Taylor polynomials with center 0 are also called Maclaurin polynomials. I don't know which came first, but I suspect the Maclaurins came first, and then the more general understanding developed later. Let's go through and see if we can analyze how to write the first 7 Maclaurin polynomials, or the Taylor polynomials with center 0, for f of x equal to sine x. You'll see that I've developed a chart for you to use here, and I will probably have to add another row. We're going to compute these by taking the nth derivative of the function and writing that function in each of these slots. Then we're going to substitute the value of the center a, which for us will be 0, into that derivative and write that number here. Remember that when you plug a constant into a function, you typically get a constant out, not another function. So this column will give us functions, and this column will give us constants. Let's proceed with the process. The first one is the nth derivative when n is 0. Remember that we defined the zeroth derivative, in fact, to represent the actual function itself. Our function, as given above, is simply sine. So the zeroth derivative is, in fact, still sine of x. Now let's go ahead and complete the derivatives before we start plugging in. Different students like to do it different ways, but I find it's easier to think in terms of derivatives all at once and then to plug in all at once. Now I want the first derivative of the function, which is the same thing as f prime of x. The derivative of sine is, of course, cosine of x. Let's find the second derivative. The second derivative, which can also be written f double prime of x, is negative sine. The third derivative, f triple prime of x, would be negative cosine. You may remember from Calculus 1 or earlier this semester when we did integration by parts that both sine and cosine repeat in a pattern that's 4 long. We should not be surprised then that the fourth derivative of the function, note the 4 must be in parentheses, would give us a positive sine of x again. Now that I know that I'm back to the repeating part, I can simply write the rest down and I don't actually have to compute them. Though of course it's not wrong if you do. And the last two would be the sixth derivative, which would be negative sine of x, and the seventh derivative, which would be, where am I in my pattern? Negative cosine of x. Okay, now that I have all of those, I want to go back to the top of the table and plug in the value of the center. When you see the word Maclaurin written, then you know that the center must be 0. That's what a Maclaurin polynomial or a Maclaurin series is. They're simply Taylor series where the center is 0. That means that I'm going to plug in 0 in place of the x here. So in the next column, and I'll do these in red, I want the zeroth derivative at 0, which is sine of 0, which is 0. Then the first derivative at 0, which is cosine of 0, which is 1. The second derivative at 0, which is negative sine of 0, is again 0. You should anticipate that since the sine of 0 is 0, every other one of these is going to 0 out, and it will. The third derivative at 0 would be negative cosine of 0, which will give us a negative 1. The fourth derivative at 0, we're back to sine of 0 again, and since sine of 0 we already know is 0, our pattern here will repeat as well. That's going to be 0. The next value is going to be 1. The sixth should be 0 again, and the seventh should be negative 1. Now that I have those written down, I need to try to remember what the formula is. Remember that the formula for P sub n can be written as the finite sum of terms from k equals 0 to n of the C sub k constants times the binomial factors x minus a raised to the kth power. You'll notice that I've used k for the index of summation so that I can use the lowercase letter n as the upper index of summation. The constants, which are the coefficients of each term, C sub k, are given by this formula right here. What I have computed in the table above is not the entire thing, but instead just the numerator of each coefficient term. I will need to divide each coefficient term by k factorial, where the k will match whichever derivative it is. Let's go ahead and write down what the different polynomials are going to be. We can start, if we want to, since we're looking for the first 7, we can actually start with the zeroth one, since the zeroth one, of course, would also work according to the pattern as well. So p sub 0 would have to be the product of c sub 0 times x minus a, which a in our case is 0, raised to the kth power. Remember that all Maclaurin polynomials and Maclaurin series have a center of a equal to 0. In this case, since our 0 is the subscript, we can replace that power with 0, which basically means that the 0th polynomial approximation is actually a constant. It's going to be a terrible approximation because a constant is just a horizontal line. And as you know, that's not a very good approximation for anything except another horizontal line. However, we can compute using this part of the formula for the constant. This has to be the 0th derivative, which is the actual function itself, at the center, which is 0, divided by 0 factorial. We know that 0 factorial is defined to be 1, and we found f of 0 at 0 to be 0. In other words, the first approximation, which is actually the 0th one, is the approximation of the horizontal line y equals 0. That is also known as the x-axis. And you have to admit the x-axis would make a terrible approximation for sine, though it's not too awful as long as you don't get very far away from the center, which is 0. Remember that your center is where it has to be close to. And of course, the function sine, if you're only looking close to 0, does stay relatively close to the horizontal line y equals 0. Now let's find P1. Remember that P1 is actually going to be given by P0 plus the next term. The next term out would be C1 times x minus a raised to the first power. This is a series, although it is a finite one, that will generate all of the terms in each Taylor or Maclaurin polynomial. This will give me, since I know that p sub 0 from the work I did before was 0, I need to find the c sub 1. C sub 1 is going to be given by f prime at 1 with the center 0 plugged in. F prime of 0 was 1. That means that I'm going to have plus 1 divided by, don't forget about 1 factorial, and then multiplied by x minus a raised to the first. Since 1 divided by 1 factorial is 1, then I can write the first approximation to sine as the line x minus a. But remember that a is the center, which is 0, so this becomes the line x. On the graph, that would be the line that goes through the origin with slope 1. Again, it's a slightly better approximation than a horizontal line, but still not a great one. Let's find P2 now. P2 is going to take P0 plus P1 and add on the next term, which would be the second coefficient times x minus the center with the second power. We know the center is 0, and we know that P0 plus P1 reduced to simply x. Our C2 constant coefficient is given by the second derivative at the center divided by 2 factorial. the second derivative at the center is 0. Since that's a 0, that is going to give us 0 divided by 2 factorial times x squared. Now 0 times anything is still 0, which means, bizarrely enough, that both the first polynomial approximation and the second polynomial approximation are the same. In fact, this pattern will continue for both sine and cosine. Every other one, of course, is going to zero out. Let's create a little more space so we can continue writing down up through the 7th polynomial approximation. Now we're ready for the 3rd polynomial approximation, P3. Remember that P3 is going to be P0 plus P1 plus, well, actually it's not P0, P1, it's C0 times the factor. So really what it comes down to is the previous approximation. So up here, this should just be P1 plus the new term. This is going to be P2 plus my new term, which is C3 times x minus a cubed. In other words, each time you expand the polynomial, you only add on one term to the previous approximating polynomial. In this case, we need to figure out the coefficient c sub 3, which will be the third derivative at the center, which was -1 divided by 3 factorial. We found that P2 was the same as P1, so I have -1 for the third derivative at the center divided by 3 factorial times x minus the center, which is 0, cubed. In general, we tend to leave the factorials on since patterns can be lost if you omit them. This is going to give us x minus 1 over 3 factorial x cubed. That would be the third approximating polynomial. Let's find the fourth. The fourth approximating polynomial would be the third approximating polynomial plus the next term, C4, x minus the center to the fourth. In our case, the center is 0, and we can write down what the third approximating polynomial was, and then add on the fourth derivative times x to the fourth. But recall that the fourth derivative was 0, so the fourth derivative divided by k with factorial, which is 4 factorial, would be 0 over 4 factorial times x to the fourth. This also goes to 0, which means that each even polynomial is not going to change the polynomial approximation. P5, however, will be different. P5 is P4 plus C5 times x minus the center, which is 0, to the fifth. P4, which was the same as P3, is x minus 1 over 3 factorial times x cubed. C5 should be the fifth derivative at the center divided by 5 factorial. So I know I have a divided by 5 factorial, and the fifth derivative is 1. That will give me a positive 1, and then an x minus a, again, to the fifth power. That will be P5. My next step, of course, is to continue with the next two. However, I know from what I've done previously that P6 will be equal to P5 because that derivative is going to be 0. Again, the sixth derivative was 0, so it doesn't actually add a new term. The seventh one will be the last one to change. And the seventh approximating polynomial would be given by the sixth approximating polynomial, which is actually the fifth, plus the seventh constant times x minus the center raised to the seventh power. P6 is x minus 1 over 3 factorial times x cubed plus 1 over 5 factorial times x to the fifth, again because the center is 0. And then the next term, I should have the negative 1 from the 7th derivative over 7 factorial times x to the 7th. You can see that by leaving it in the factorial form, I can see the pattern developing. I can see that the pattern now is that the signs alternate and the powers are odd numbers beginning with 1. And the denominators are also factorials on the odd numbers beginning at 1. Now let's take a look at this graph, which represents some of these different approximations to sine. Sine is the graph you see here in black, and you'll see that P7 is in green, P5 is in blue, and I believe P3 is the one in red. When you're looking at that then, what you have here, if I can move that up a little bit, what you have here are the approximations. Notice that as the number of derivatives you had matched increased, in other words, the more terms in your polynomial, the further out it is a good approximation for the function. Let's try to match the color that we see on the functions to how far out it's a good approximation. For P3, I can see the first place it sort of starts to go away is about here on the left and about here on the right. P5 is in blue, and I don't know if I really have a very good blue, but I'll try this one. In blue, it looks like I can see a difference maybe here and maybe here. You can see that I can get much further away from the center 0, and I still have a decent approximation with P sub 5. P sub 7 is the best. The green one is a much better approximation. I can't really see the difference until I get to about here on the left and about here on the right. In other words, P sub 7 is a pretty good approximation between negative pi and pi. That's actually quite far from the center 0. And you can imagine that as we increase these, it would become an even closer and closer approximation. Let's now look at example 2. In example 2, we are asked to find the first 7 Taylor polynomials for sine x again, but centered this time at pi divided by 2. What is this going to change from the chart that we drew above? It no longer says Maclaurin, so the center is not 0. The derivatives here will not change. However, the center value will change since the center is now pi over 2. The constants in the last column will all be different. Go ahead and pause the video now and see if you can compute the first 7 Taylor polynomials. Then turn the video back on and we'll check our answers together. Let's examine the results for the first 7 Taylor polynomials for sine of x centered at x equal pi divided by 2. The functions in the column for the nth derivative have not changed from the previous. The derivatives are exactly what they were before in a repeating pattern of 4, sine, cosine, negative cosine, and then repeating, sine, cosine, negative cosine. However, our center has changed. It's a Taylor polynomial, which is centered at pi over 2. We'll substitute pi over 2 in place, and that will give us a repeating pattern of 4 of 1, 0, -1, 0. And again, then it repeats 1, 0, -1, 0. These form the numerator of the coefficient of each term in the expansion. Here below, you'll see the first 4 Taylor polynomials for sine of x centered at pi over 2. That means that these polynomials are decent approximations to the sine function, provided you're close to the value pi divided by 2, which is about 1.57. The zeroth polynomial is just the function we started with, which is sine x. Again, it does fit the pattern since the zeroth derivative at pi over 2 is 1 and 0 factorial is 1 and x minus pi over 2 to the zeroth is 1, I do end up with sine of x. P1 is that term plus the next term. It's the constant c sub 1 times x minus pi over 2 to the first. I went ahead and worked this out, though I knew it was going to zero out, because the second repeating pattern when I plug in the center was a 0. That makes the numerator of the fraction for the coefficient 0, though it's divided by 1 factorial and multiplied by x minus pi over 2 to the first power. This means that this term zeroes out and it becomes exactly what p sub 0 was, which is just the sine x original function. For p2 then, we will take p1 and add the next term, the quadratic term. To find c sub 2, you need to find the second derivative at pi over 2. Scrolling up, the second derivative at pi over 2 gives us a negative 1. That becomes the numerator of that coefficient, and it's divided by 2 factorial, with the 2 matching the number of the derivative and the power on x minus pi over 2. Notice that P3 will be the same as P2 since the third derivative gives us a 0 again. P sub 4 begins the pattern over. The pattern was 1, 0, negative 1, 1. This begins again with 1. That means the fourth term will have a 1 in the numerator divided by 4 factorial times x minus pi over 2 to the fourth power. The 1 again came from the fourth derivative evaluated at the center. The final three, P5, P6, and P7, can be found here. P5 and P7 will reduce to becoming whatever the previous polynomial was, since the fifth derivative at the center and the seventh derivative at the center are also 0. The sixth derivative at the center is negative 1, which is why we get a negative 1 in the numerator of the coefficient. This is for the sixth derivative at pi over 2. Divide by 6 factorial times x minus pi over 2 to the sixth power. This will be a much better approximation than the previous ones because it has more terms, and it will be a better approximation over a wider interval. Let's take a look at another problem. This problem is number 3. Find the first 4 Maclaurin polynomials P1, P2, P3, and P4 for the function natural log of x. Again, take a moment, turn off the video, and at least find the derivatives. We'll turn the video back on after you've found the derivatives and before we plug in the center. You'll see in the first row that I've written the zeroth derivative, which is actually the function itself, and the function was given to us as the natural log of x. The first derivative is the derivative of natural log, which is 1 over x. I wrote it in its exponential form with a negative 1 for the power to make it easier to do the subsequent derivatives. The second derivative is negative 1x to the negative 2 using the power rule on this form. I rewrote it as negative 1 over x squared to make the next step easier to plug in. The third derivative, again I applied the derivative to the power form, which gave me a positive 2x to the negative 3, or positive 2 divided by x cubed. Taking the derivative again, I get negative 6x to the negative 4, which is a negative 6 divided by x to the fourth. What is the center for this polynomial? Note that we have the word Maclaurin in the directions. When it says Maclaurin, that means that the center, often written as lowercase letter a, is 0. Take a moment now, stop the video, and complete the rest of the chart by plugging the center 0 in and see what happens. Hopefully you haven't been gone for very long. The problem is You can't have 0 as a center for a natural log function. The natural log is not defined at 0. And if you look at all of these derivatives, that should have been clear to you, since if you try to plug 0 into any of these, you will have something that's undefined. In other words, I set you up at the beginning to have something that couldn't possibly work. So again, the point of this is whatever the center is should be in the domain of the original function. Let's look at this function again and change the word from Maclaurin to Taylor and shift the center away from a equals 0. In this case, let's choose perhaps the number 1 for the center. If I rewrite this problem and make this now a Taylor polynomial with center not 0 but center equal 1, let's see if we can come up with an expression for that. You may want to pause the video again and fill in the rest of the chart, now assuming that instead of a Maclaurin polynomial, you have a Taylor polynomial with center at 1. Since I have rewritten the problem to now be a Taylor polynomial with center of 1, you'll see that when I plug in the 1 for the original function, I get a value of 0. After that, the first derivative, which is 1 over x, gives me 1 over 1, which is 1. The second derivative, negative 1 divided by x squared, results in negative 1. The third derivative, 2 divided by x cubed, results in 2. And the fourth derivative, negative 6 divided by x to the fourth power, results in negative 6. Take a moment and pause the video and write down what you believe to be the first 4 Taylor polynomials for natural log of x centered at the value a equal 1. Here are the first 3 Taylor polynomials for natural log of x with center at x equal to 1 or a equal to 1. The first, of course, is the zeroth polynomial, which is the function itself, evaluated at the center, which is, of course, 0. This is just, again, the x-axis. If you think about the graph of natural log, what we have going on here is the natural log is curving up like this. P sub 0 is, of course, just the x-axis, which is this line here. That's P sub 0. Now look at P sub 1. P sub 1 comes from the first constant, which is the first derivative evaluated at 1 divided by 1 factorial times x minus 1 raised to the first power. Remember up here that when we found our pattern for the derivatives, we didn't get a repeating pattern like you do with sine and cosine. Instead, you have 0, then 1. So the numerator coefficient will be 1. For the second derivative, we'll have a negative 1. When we look at the second derivative, it's p1 plus the quadratic term. The numerator is negative 1 divided by 2 factorial times x minus the center 1 raised to the second power. P1 is the graph of the line x minus 1. If we were to graph that line, it would probably look something like that, which, yes, is a fairly close approximation, again noting that we are looking at the point where x equal 1. The point where x equal 1 is, of course, right here on the axis where they all touch. P3 is going to be a cubic. In this case, we add on one more term, which will give us 2 over 3 factorial x minus 1 cubed. P4 adds yet another term, the 4th degree term, which will give us 6 over 4 factorial x minus 1 to the 4th. There is, in fact, a predictable pattern here. It's a bit hidden because we wrote the derivatives as 2 and 6. If we go back up here to what we have in the original, if we were to continue to take derivatives, you would see that the first is in fact 1 factorial, and then 2 factorial, and then 3 factorial because the 3 was brought to multiply by the 2. The next derivative will bring a 4 to multiply by the 3 and the 2 and the 1, which means the next one, of course, will be 4 factorial. So there is, in fact, another hidden pattern here. It's often the case with sequences in series that multiplying out the constants actually makes the problem more difficult and the pattern harder to see. Let's take a look at the last example for this video. This is example 4. Find the first 7 Taylor polynomials for the exponential e to the x power, but centered at the natural log of 2. Let's take a look at what this one might look like. In order to do this one, we're supposed to find the first 7 polynomials for e to the x at the center, natural log of 2. When we look at e to the x is a rather special function, one of our favorites in fact, because the derivative of e to the x is always, yeah, you got it, e to the x, which means that no matter what I do and how many times I take the derivative, I'm always going to have e to the x in the first column. This means that all my derivatives are e to the x. So you can go ahead and fill in the rest of the chart with all of that column representing the derivative of that number of e to the x being, in fact, still e to the x. Then let's figure out what will happen when we plug in the rest. I see that I am short one row, so let me add another row here. And this will be the 7th. So this will give me the 7th derivative at x, which is still e to the x. What happens now when I try to plug in the center value, which was the natural log of 2? Since all my derivatives are e to the x, when I plug in the center, I should get the same constant every time. So since I know that, I only need to plug it in once and then just write the constant all the way down the column. What would the zeroth derivative, which of course is just the function, at the natural log of 2 be? This is e to the natural log of 2, which is just 2, which means they are all 2, which means coming down all the way down the second column, they're all the value of 2. Now we can write the first 7 Taylor polynomials. Again, we're using the formula that you see at the bottom of the screen, where the p sub n is the finite sum of terms with c sub k representing the kth constant coefficient, and e minus the center is raised to the kth power. In this case, if I'm looking at p sub 0, I know that the value came out to be 2, and it is, of course, divided by 0 factorial and multiplied by x minus the natural log of 2 to the 0th power, which is still 2. That means that p1, which is p0 plus c1 times x minus the natural log of 2 to the first power. And then I can figure out what c1 is, but c1 is the kth derivative, in this case the first derivative at natural log of 2 divided by 1 factorial, which is just going to be 2 for p0, 2 for the first derivative divided by 1 factorial x minus the natural log of 2. This leads to 2 plus 2 times x minus the natural log of 2. What about the rest? Take a moment, pause the video, and write them out for yourself. You'll see here that I've written out the first 3 approximations, with the 0th being the first. P1 and P2 are the linear approximation and the quadratic approximation. P3 is the cubic approximation, and P4 is the 4th degree. I got tired of writing, so I stopped after p sub 5. But I'm sure you've got the pattern and you could write down the last 2, p sub 6 and p sub 7, for yourselves. Let's take a moment now and think about what we can do with these and see how we can evaluate how accurate they are. Use the third example to approximate the natural log of 1.2 using p sub 4. You'll see in front of you again that this is example 3, where we were approximating the natural log of x with the 4 Taylor polynomials. We're going to use p sub 4 to approximate the natural log of 1.2. To approximate the natural log of 1.2, I will need to plug in 1.2 in place of x. This means I'm evaluating p4 of 1.2. This becomes 1.2 minus 1 minus 1 over 2 factorial, which is 2, times 1.2 minus 1, which of course will give me 0.2, raised to the second power, plus 2 divided by 3 factorial, which is 6, times another 0.2 raised to the third power, minus 6 divided by 4 factorial, which is 24, times another 0.2 raised to the fourth power. Take a moment to grab your calculator, crunch out these numbers, and see what you get for your approximation. When I was done with the calculations, I got the fraction 1,367 divided by 7,500. This equals the repeating decimal 0.18226 repeating. Now take your calculator and calculate the natural log of 1.2. It will almost certainly be irrational, but the calculator will give you a good approximation, accurate to many more decimal places than what will show on the screen. When I did this calculation, I got 0.182321556 and so forth. You'll notice that these are exactly correct up to the third decimal place within 1/1000th, and they aren't off until the fourth decimal place in the 10,000th place. In other words, we were able to get a very accurate evaluation for the natural log of 1.2 using a simple polynomial expression. This is nothing more than adding, subtracting, multiplying, dividing, and using powers. This is one of the reasons that we teach Taylor polynomials. They can be used to approximate all kinds of functions in all kinds of situations, and they provide very good approximations. We're going to stop this video here, but we are by no means done with this particular section on Taylor and Maclaurin series. Thus far, we have only talked about Taylor and Maclaurin polynomials. You might imagine that if you allowed the number of terms to go to infinity, instead of stopping at a finite number, that you would in fact get a series instead of a polynomial. Or in other words, you'd have an infinite polynomial. In the next video covering section 6.3, we will do exactly that and take a look at Taylor and Maclaurin series. This ends this video.